Hello, so in this part of our review jigsaw, we are talking about atomic structure and types of matter. And honestly, probably one of the most important things of this is going to be this very first part on Coulomb's law. So Coulomb's law is a relationship between attraction and repulsion. So like charges are going to repel, opposite charges attract. So in terms of chemistry, the charged particles we're looking at are going to be those protons and electrons, and we're those subatomic particles, and we're looking at that attraction and repulsion between them. So here is what Coulomb's law looks like. Sometimes you'll see a F there instead of that E for force rather than E for energy. But it's the energy or force of attraction between the particles, and it's proportional to the charge of your two particles. So we have the charge of the first particle times the charge of the second particle over the distance or the radius between the charged particles. So we can see here that if those values of Q increase, that's going to cause the value of E to increase as well. So whenever we have a greater magnitude of our charged particles, whatever they are, we're going to have a greater force of attraction. However, radius is in the denominator. So the radius is going to have an inverse relationship with that charge. If our radius is decreased, well, now we're dividing by a smaller number. That's going to make our force of attraction increase. So the closer together these particles are, the more they're going to attract or repel each other due to that decreased distance. So again, in short, the big things to know here: energy of attraction or repulsion is going to increase as the size of those charges increase as well. So we had that direct relationship between the magnitude of the charge and that force of attraction. When we're looking at the radius piece of this, as we decrease the radius, that's when we're going to have the greater energy of attraction. So again, we had that inverse relationship between those two pieces. So let's think about this. If we have an electron, is it going to be more attracted to the nucleus of a hydrogen atom or a helium atom? Well, a hydrogen atom only has, a hydrogen atom only has one proton, whereas a helium atom has two protons, and then we have just the one single electron here. And assuming we're at the same distance, we're looking at the magnitude of charge. Well, since helium has two protons in its nucleus, it's going to have the greater magnitude of charge. So we can write up a little synopsis of that. So I said helium because it has two protons compared to hydrogen's one proton, meaning there is a greater magnitude of charge and thus more attraction between the electron and the helium nucleus. Definitely feel free on things like this to kind of abbreviate, especially those common symbols like that proton, that P plus symbol, or because. Things like that is totally okay. Alright, so we got a few more examples here. So take a minute, think about those, and then continue the video and we'll talk about the correct answers real quick. And so when it comes to attraction, again, the things we're looking at is that magnitude of charge and then the radius. So in 1A, B is going to have a greater attraction because in B we have a greater magnitude of charge. I have 2 plus attracting to minus 1 as opposed to plus 1 attracting to minus 1. That 2 plus is basically like a stronger magnet. The larger that charge is, the stronger that magnet is, the more they're going to be attracted. If we're looking at part B, A is going to be more attracted because it has a smaller radius, so the closer together they are, the more attracted they'll be as well. So magnets, you can feel, like if you're holding a magnet up to the fridge, you can feel that attraction, that force, that pull start to happen as you get closer, but when you're really far away, you don't really feel it. So the closer you get, the more attraction that we have. Part C, A is going to be more attraction because D is actually a force of repulsion. We have like charges there, like charges are going to repel each other. Then lastly, number 2, an electron which has a -1 charge is going to be most attracted to B. B has a positive charge, which is the greatest charge out of all those. And we don't care about the neutrons. Neutrons are neutral. They're not part of this whole attractive and repulsing game. So we talked a little bit here about protons, electrons, and neutrons. We're going to talk more about that and how they make up the atom. First off, atoms make up matter, and matter is anything that has mass and takes up space, or has mass and volume. And again, all this matter is made out of atoms. In the atom, we have 2 main regions. We have the nucleus. So the nucleus is in the center of the atom. It is very, very small and very, very dense. Essentially, all the mass of the atom is in this little tiny nucleus. The other part would be the electron cloud. So the electron cloud is all around the atom, and it's mostly empty space. That's where our electrons are. If we're like comparing the size of the nucleus to the electron cloud, it would be like a tennis ball in the middle of a football field, where the tennis ball is the nucleus. And again, that's where all the mass of the atom is, in that tiny little tennis ball in the middle of this giant football field, where the rest of this football field is mostly empty space with a few massless electrons floating around. So let's talk more about these 3 subatomic particles that make up our atom. We have protons, neutrons, and electrons. We've seen a couple of these symbols before. Electron, we use E-, proton a P positive, and neutron an N. Sometimes we put that little 0 up there. In the nucleus, we have our protons and neutrons, and then the electrons are out in the electron cloud. As we said, talking about Coulomb's law, protons have a positive charge, neutrons are neutral, electrons are negative. We've also said that all the mass of the atom is in the nucleus. So, protons have a mass of about 1 AMU. Neutrons are also about 1 AMU, where electrons are essentially massless. Their mass is so tiny we consider it negligible and just say that they have 0 mass. The units that we use for these is AMU, so we just saw that, the atomic mass unit. So the atomic mass unit is actually 1/12 the mass of a carbon-12 atom, or 1/12 the mass of a carbon atom that has 6 protons and 6 neutrons. So that is what that's defined as. So a lot of this information for specific atoms, like how many protons, neutrons, electrons, can be found using the periodic table. So looking at the periodic table, we see this number up top. That big whole number is the atomic number. It tells us the identity of the element and the number of protons. In neutral atoms, the number of protons is also equal to the number of electrons. The other decimal number that you see on there is the average atomic mass. It's an average mass of all the elements' isotopes. If you want to know the mass of just one single isotope, that's going to be the number of protons plus the number of neutrons. So more on that to come. The symbol is our little shortened name, 2 letters, 1 or 2 letters. The first letter is always capitalized, and then the name is just the full-on name, and we do not capitalize that. Okay, so as we said, more to come on isotopes. So here we are. An isotope is when we have an atom of the same element, but it has a different mass. If it's the same element, it must have the same number, the same element, it must mean it has the same number of protons, but it has different masses. It has different masses due to a different number of neutrons. So neutrons, those neutral particles inside that atom in the nucleus there. To find the mass of a specific isotope, like we said, it's the number of protons plus the number of neutrons. These are the only 2 subatomic particles in the atom that have mass, so we're just going to add them up. We can designate isotopes two different ways. We have the hyphen notation and then the isotope notation or nuclide notation, where we have the subscript and superscript to the left of our symbol, as you see there. Looking at the hyphen notation, we have the name and then a hyphen and then a number. That number is the mass number. So when I say carbon 12, that means that I have 12 combined protons and neutrons there. So we could also have carbon 14 or chlorine 37. So again, those are the mass numbers, which is the total number of protons plus neutrons. In the isotope notation, we have the mass number as a superscript and the atomic number as a subscript to the left side of that symbol. So if we wrote that for carbon 14, the mass number is 14, that goes as our superscript. Carbon always has an atomic number of 6. If it does not have an atomic number of 6, it is not carbon. Again, that identifies our element there. And then for chlorine, we said it was a mass 37, so 37 protons plus neutrons, and chlorine is atomic number 17. So 17 plus 20 would give us that 37 mass number, meaning we have 20 neutrons in there. On the remainder of this page, page 10, there's a little bit of practice and examples with our isotopes. Take a moment, pause, try those out if you feel like you need to. Resume for the answers. Okay, so we can see here at the top, looking at set 1, they are both carbon, it's the same element, so we have the same number of protons. But that mass number, one's 12, one's 13. So they have a different mass or mass number because the number of neutrons is different. Carbon 12 has 6 neutrons, while carbon 13 has 7 neutrons. Doesn't change the identity, just gives it a bit more mass. So those similarities and differences would be true for set 2 as well. On the bottom, we were writing the different notations and identifying the number of protons, neutrons, electrons, etc. So again, after the hyphen, that's always our mass number. So we can see that all those are matching. Mass number is also on top here. The atomic number is going to be this bottom number here. So atomic number, we can see all matches. Atomic number is equal to the number of protons, which is also equal to the number of electrons. Again, that mass number was after the hyphen there, and mass number is going to be protons plus neutrons. So protons plus neutrons will equal that mass number there. So that wraps up our little talk on atomic structure. There is another video talking about how to calculate the average atomic mass, which is that decimal number. It's different than mass number, so be sure you know how to do that. Here we're continuing on to talk about matter and our different types of matter. Matter is anything that has mass and takes up space. And it can have different components that make it up. So depending on what makes up our different things or matter that we have in the world, it gets a classification. So we have this table that kind of goes through, and the first big separation of matter is going to be separating between pure substances and mixtures. Pure substances cannot be physically separated. That's because they have one single chemical composition. And there's two different types of pure substances. Those pure substances are going to be an element and a compound. Well, if we have a pure substance, some of them can be chemically separated into simpler substances, and that's our compounds. So compounds are made up of two or more elements, and we can chemically break those apart into its elements. Elements is the simplest form of matter. It is a pure substance because it's only one single composition. So if we look at some of our examples of elements, which is anything on the periodic table, we can see things like sodium, titanium, or oxygen gas. So something like sodium, if you have a piece of sodium every single smallest piece of matter in there is a sodium atom. It's all one single fixed composition. Same for titanium. Same for oxygen. Even though oxygen's one of our diatomic elements, hence why it's O2, it naturally exists in that pair, there is still only one single building block of matter, that being the oxygen atom. Compounds, again, are going to be two or more elements put together. So we have a few examples there. We've got water, glucose, and salt there. So we can see multiple elements put together. Well, we can separate those into its elements chemically. You can apply electricity to water and it will generate hydrogen gas and oxygen gas, thus splitting it up into its elements. Another thing about compounds versus elements, compounds do not have the same chemical properties as the elements that is made from. For example, NaCl is made from sodium and chlorine. Sodium is a soft silvery metal that's highly combustive in water, and chlorine is a yellow-green toxic gas. But put those together, we get this white crystal table salt that we eat every single day. So compounds and their properties are nothing like the elements that it's made from. So those are our pure substances, a single fixed composition, which is true for our compounds as well, because if you have water, like we see in this picture here, every single smallest piece of our water looks exactly the same. We can separate, if we can separate matter physically, then it becomes a mixture. Mixtures, we have two different types depending on if they're uniform throughout. If it is not uniform throughout, we get a heterogeneous mixture, that prefix hetero meaning different. So if we look at this picture here, we can see that these compounds down here, they got the gray and the red. This has the white and the red. Those are two different things. And it's also not uniform throughout. All the gray ones are at the bottom and the white ones are at the top there. Let's talk about a few other examples of a heterogeneous mixture. Those could be things like granite. Granite is made up of lots of different rocks and minerals, and when you look at a piece of granite or slab of granite, you can see all those different parts and the different properties that they have. Some of it are going to be a lighter color, some's darker, etc. Same for a salad. You look at it, you see all the different parts. There's my lettuce, there's my tomato, chocolate chip cookie, same idea. If it does look uniform throughout, that is a homogeneous mixture, or another word for that is a solution. So when you look at this picture here, we can see that all of these different molecules within here are uniformly spread throughout the whole mixture. So this could be something like sugar water, where these big old molecules are sugar within all these little water molecules. But if you have sugar water and you're looking at it, you can't pick out which individual pieces are sugar versus which individual pieces are the water. Couple other examples could include air, milk, and salt water. So air is made up of lots of different gases. It's mostly nitrogen and oxygen, but it's got some carbon dioxide in there, a little bit of helium, carbon monoxide, and trace amounts. But if we look at air, we don't see the different parts. We can't distinguish between the oxygen and the nitrogen. Milk also has lots of different chemicals in there. You got your fats, you got the water, etc., the lactose, but we don't see the different parts. And then salt water would be similar to that sugar water there. So let's look a little bit more in depth at these different types of matter. So again, pure substances can only be separated chemically. They have the same or a fixed composition. They're made of only one single unit. So elements are made up of one single type of atom, so our building blocks there, that's anything found on the periodic table. One thing about elements though, they cannot be broken down. They're still going to maintain their identity. One more note on our elements is our diatomic elements. They're still made up of one single building block. So our H2, O2, etc., Brinkelhoff, though there's two atoms, is still just one type of atom there. Compounds are going to be two or more elements in, again, fixed definite portions. though, so we have that one single fixed composition. They cannot be separated by physical means, but they can be separated chemically. Another really important note that we briefly touched on, properties of the compound are completely different than the individual elements. So again, something like sodium and chlorine coming together to make NaCl. We got a soft silvery metal, highly combustible with water, a yellow-green toxic gas, and we make table salt that we eat every day. Completely different properties. But if we have our compound salt, within that white crystally salt, every single smallest piece of it is that fixed NaCl composition, making it a pure substance. Mixtures can be separated by physical means. So when two or more substances are physically combined, it doesn't matter what state of matter they are, and each substance within that retains its own unique property. So something like granite, we see the different colors, the different textures, crystal structures of the different minerals that are in there. Again, granite is a heterogeneous mixture where the parts are not evenly distributed, so it does not look the same throughout. Homogeneous mixtures, we do have that uniform distribution, and we can call those a solution there. But if we have something like air, each gas within air is still retaining its own individual properties. Oxygen versus carbon dioxide are very different gases within this same mixture. Anytime we have a mixture, we can separate it through physical means. There's a couple means to be familiar with. One, the first would be filtration. So filtration, we're taking a solid liquid mixture, we're pouring it through a filter paper. The filter paper is designed so that all the solid is going to get stuck up in that funnel, allowing the liquid to drain through. Yay, you separated your solid and your liquid. Another method would be distillation. So distillation is the process of taking a mixture of two liquids. So you have a mixture of two liquids down here in this flask. We can see that there's heat, there's flame coming out of it. That's going to cause the more volatile compound to boil first. So it has a lower boiling point. So it's going to boil, it's going to travel up here as a gas, and then it's going to go into the condensing tube as a gas. And as it's in that condensing tube, which has cold water going through it, it's going to turn back into a liquid and go down into this bottom tube. All the while, that second liquid in this first flask never boiled. It's still sitting there. Okay, the very last form, and we'll talk about more as the year goes on, is paper chromatography. So paper chromatography has to do with the different attractions that the substances in the mixture have for the solvent versus the versus the paper. The solvent is the liquid that's down here. So kind of like if you stick the end of a paper towel into the liquid, it's going to absorb and move up. Same sort of idea. We stick the end into there, that liquid is going to absorb and move up the page. As it absorbs and moves up the page, we can see that it spread out all the different components of that ink spot. The components that stay at the bottom, so like that gray spot was stationary. It didn't move very much, like the paper was stationary. So it was more attracted to the paper and did not move. Whereas this yellow spot up here, it moved a lot. It was mobile like the solvent is mobile. So it is more attracted to the solvent, so it kept moving with the solvent rather than staying still on the paper. Okay, so that's a kind of synopsis on types of matter, structure of the atom. Make sure you're familiar with these things. Try out the extra jigsaw practice as well if you feel you need more practice.